Rates are a fundamental aspect of chemistry. They are defined by the change in concentration over the change in time. From this, we can tell that the units are mole, decimeter to the minus 3, seconds to the minus 1. Often, when you change the concentration of a reactant, you change the rate. Just a quick side note. When I write brackets X, this means concentration of X. X could be a reactant or it could be a product. So the rate is often proportional to the concentration. Each concentration also has an order of reaction. The order of reaction is basically the power that the reactant is raised to. This could be 0, 1, 2, so on and so forth. The order of reaction influences how much a change in the concentration of the reactant changes the rate of the reaction. For example, if I had concentration of A, and we know that A is a first order reactant, if I doubled the concentration, I would double my rate of reaction. If A was a second order reactant, if I double the concentration, my rate would quadruple. A special case you need to be aware of is if you have a zero order reactant. No matter what factor you multiply the concentration by, your rate will stay constant. You might come across something called the rate equation. The rate equation ties together rates of reaction, concentration of reactants, and the order of reaction. It often takes on the form rate is equal to K, concentration of reactant A to its power, and concentration of reactant B to its power. This equation helps us calculate the reaction at a specific concentration of reactants. K is a proportionality constant that relates the concentration of the reactants to the rate. You might also hear about a thing called the overall order, and that's basically all the orders of reaction added together. So in that case, the overall order would be M plus N. Another quick thing to mention, if you have 3 or more reactants, you would also have C to its power and so on. You can determine the order of a reactant either with a graph or with a table. Let's start off with the graph method. Each rate versus concentration graph has a specific shape that you can recognize. For a zero order reactant, the graph would be a flat line. And actually, you can determine K, as K is just the y-intercept of this line. For a first order reactant, the shape of the graph is a straight line through the origin. To determine K, it's the change in Y over the change in X. Now, for a second order reactant, it's a bit harder. It's actually an X squared curve. I already mentioned this before. First order reactant, if you double the concentration, you double the rate, so it's a linear relationship. For the second order reactant, if you double the concentration, the rate quadruples because it's times by 2 squared. That's why it's an x squared curve. The reaction constant, K, is the gradient for the first and second order curve. But for the second order curve, if you want to take the gradient, you actually have to plot rate against concentration squared. That turns the curve into a straight line where change in y over change in x is equal to the constant. The table method is a bit harder to determine the rate with. Let's say you had a table like this one and it asks you to find the rate equation. To find the rate equation, you have to find the individual rates of the reactants. So let's start off with A. You can see that between experiments 1 and 2, the concentration of A doubles. And subsequently, the rate doubles. And we know this is a direct result of the concentration of A changing, because the concentration of B has stayed constant between experiments 1 and 2. Since the rate doubles and the concentration of A doubles, we can say that the rate is directly proportional to the concentration of A. Hence, A is first order. We can do the exact same thing for B actually. We know that between experiments 1 and 2, concentration of B doubles, but this time the rate quadruples. We know this is a direct result of the concentration of B changing because the concentration of A has stayed the same. From this, we can conclude that the rate is proportional to concentration of B squared. Hence, B is second order. Now that we have the individual orders of a reactants, we can write the rate equation. Rate is equal to K, A to the 1, you don't really have to write this one, B squared. Now for a slightly harder problem, again we start with finding the concentration, the order of A. Between experiments 1 and 2, concentration of A doubles. Rate also subsequently doubles. B stays the same, so we know that the rate is directly proportional to the concentration of A, so A is a first order reactant. Now we do the same for B. From experiment 2 to experiment 3, concentration doubles, but this time so does the concentration of A. Subsequently, rate increases by 8 times, 8-fold. Now this is a bit trickier because they're both increasing. However, we know that A is a first order reactant, so if A doubles, so will the rate. We can take this into account and double 0.2, our rate from experiment number 2, to find our intermediate. Now that we've taken into account the effect of A on the rate, all the effects on the rate will be from B doubling. So we know from 0.4, our intermediate, to 1.6 in experiment 3, the rate quadruples. So we know that when concentration of B doubles, the rate quadruples. Hence, concentration of B squared is proportional to the rate, and B is a second order reactant. Hope you enjoyed. This was lesson 3.